Okay, so the second part of the lecture will deal with the finite difference method. So in the morning, we saw that we could derive differential equations that describe the motion of a beam or a cable or a beam on elastic foundations. And as I said, in the literature, you can find, for example, if you're interested in this topic, then you can find very good books, like, for example, the book of Timoshenko, where he derives the equation of motion in a differential form for quite many different kind of beams and systems. Okay, so as you saw in the previous lecture, we could analytically calculate the frequencies for these systems. Now, as the problem get more and more complicated, the boundary conditions and so on and so forth, we can no longer solve this analytically. We have to treat this using some kind of a numerical method. Now, we can use, of course, differential equations and solve this in finite elements or in finite difference. In this course, we will have a look at the finite difference, as this is a very powerful way of solving differential equations. This can be applied, of course, not only on dynamic problems. Finite difference method can be applied on any differential equation. For example, solving, let's say, buckling of a column or any other kind of civil engineering problems. And you'll see it's quite a straightforward, simple method that can be applied. So we have the differential equation, for example, this one for a beam in bending. There's no normal force in this. This is a simple one with bending. And this can be solved with the finite difference method. We can, of course, using the finite difference method, analyze more complicated problems where we have the stiffness is a function of x, for example, and the loading is a function of x, the mass is a function of x, and also complicated boundary conditions. All of this can be solved with the finite difference method, of course, as well as the finite element method. The idea is the same, is that we apply separation of variables and use the mode superposition technique. So we say that the y can be the summation of the mode shapes. Now I have called mode shapes in this parameter z and mode shape number I, and then as an in time function. So the response can be for mode number I can be treated like this. The time function can be cosine and sine. And as we learned before, we can differentiate this twice with respect to time and with respect to space, x, and put it in the differential equation, this one. So we replace u with this. And when we differentiate with respect to x, we differentiate the z. So it's d4z, dx4. And when we differentiate with respect to time, we will then differentiate this time function. And as it is sine and cosine, when we differentiate twice, the cosine will be cosine again, and the sine will be sine again, but we will have a minus in front, and we will have an omega square in front. And this is what you see here. So by doing this, the plus will be minus, and then we will have the function again, but we will have an omega to the power of 2 for that mode I. So this is, we have seen this also from previous lectures. This is what we can do. Now, what is the finite differences? Well, I think all of you remember from one of the first years in your education when you looked at central difference approximations. The simplest one in the center of the central difference approximation is this one. When you want to calculate the slope at a point, if you want to calculate the slope at this point, Zj, you can, if you have divided this curve into segments of edge length, you can take this point minus the height of this point minus the height of that point will give you this distance, and divide this with this distance, which is 2h, okay? And then you can calculate the slope, dz dx. In a similar way, you can calculate the second derivative, the third, the fourth derivative, and so on. You will find these formulas in handbooks. And of course, the smaller the size of the segment, the smaller will be the error, okay? Okay, so what we're gonna do now is that we will replace these derivatives, or this derivative, with its approximation. It's as simple as that, okay? So this is the equation we had. Z is the mode shape. And what we will do is that, well, this is exactly the same equation. I have moved this to the right-hand side, and I have moved the EI to this side as well. And then I have replaced this fourth derivative with this one, with this function. Okay, so that's this. So this means that Z, now remember here, now the I is the mode number in this, and the J is the point number or the node number along the beam. Okay. This is the same equation I have just multiplied on this side with the size of the sigma to the power of 4. And when we do, we'll have a look at an example. Normally I will do this example on the board, but I will show you the solution and we go through it very soon. But the thing is that when we do this, we'll end up with a very nice solution that will be done by this matrix A. So we'll see how to do this. When we put all of these equations for each and every node number along the beam, we will be able to formulate the problem in this way. This is an eigenvalue problem where A is this matrix, almost always the same format in the matrix. Z is the vector of the mode shapes. And the lambda will contain the frequencies, okay? So lambda is this one. Actually, this is the lambda. We have replaced this with the lambda, as you see here. So lambda is m to the power of 4 ei omega to the power of 2. So this is our lambda. We will get the lambda in the diagonals of this matrix. So what we do is that we will construct this matrix A, and then we will send it to the Eik function in MATLAB, and the result will be the mode shapes and the eigenfrequencies. What is particular about this matrix A, as you will see soon, is that always the first off diagonals have a number 4, and always the second off diagonal have a number 1. The rest will be zeros, okay? This first and the last will, that is C1, will always be 5 if we have simply supported problem, simply supported beam. And then C2, C3, all of these will have a number 6, okay? And the size of this, if we discretize the beam into n segments, the size of this will be n minus 1 by n minus 1, as well as this one. So we will have n minus 1 number of eigenmodes and eigenfrequencies. Okay. So as I said, depending on the problem, if we want to analyze a beam with a clamped ends, then the 5 should be replaced with a 7. But we can also analyze more complicated beams, for example, beams which has a torsional spring at the boundary, a torsional spring Km. Then we will replace the 5 with this expression, where the eta is a function of the spring stiffness. All of these can be derived depending on the boundary condition. I will show you how to derive the one for the 5, how we get the 5. But the same thing can be done if we have a clamped end, just that we consider different boundary condition. Okay. So how do we get how do we consider the boundary condition? Well, actually, if this is our beam going from j equal 1, equal 2, j equal 3, and so on, for simply supported beam, then we know that the moment at 1 is equal to 0, and the moment is the second derivative of the z, of the displacement. And then we can replace the second derivative with this expression, zj plus 1 minus zj2 plus zj minus 1, okay? So we can replace it with this, and this should be equal to 0. And we write this for point number 1, okay? So this is zj plus 1, it will be j2, z2, and minus 2 zj, which is 0 actually, because we have a simply supported point. And then zj minus 1, this is z0. This is actually, as you can see, this is a fictitious point which lies outside of the beam. We say this is a fictitious point, z0. And this should be 0, which means that z0 should be the same as z2 with a minus, okay? So this says that z, the fictitious point, has the same as the point, the first point inside the beam, but with a minus sign. And this is not so strange. Imagine that this is a simply supported, and it's bending like this, okay? And because this is simply supported, the slope here should be the same. It will go up here. So this value here at this fictitious point should be the same as this, but the opposite side, okay? So this is how we can get an expression for the points, the fictitious points that lie outside of the beam. The same thing if we had a clamped, if we have a clamped here, then we can also, instead of having an equation for the moment equal to 0, we can put an equation for the slope equal to 0, okay? And then we replace the slope with its derivatives, and we can get a relation between the point outside with a point inside in the same manner. Let's have a look, just to make this more clear, we can have a look at an example. Let's have a look at this simply supported beam, which I have divided into 1, 2, 3, 4 segments, equal segments, 4 equal segments. So this node is 1, this is 2, 3, 4, and 5. We have 5 nodes, 4 segments. And it's a constant stiffness and constant mass. So this is a differential equation for this in bending. This can be rewritten as this, as we saw, by saying that u is a function of z multiplied with the time function theta, and differentiating twice, we can get this expression. Okay, and now we start to write the equations for all these points, replacing the derivative with the central difference. So j equal 1. This is actually a non-interesting point because we know that the displacement is 0. So z1 is 0. J equal 5, the same. So these are not interesting. Point 2. Well, we write the expression for this. Point 2, it's z4, which is, go back here. So the fourth derivative. So this is zj plus 2. Okay, so j is number 2. 2 plus 2 is 4. And then minus 4z3. So 2 plus 1 is 3. Minus 4z3 plus 6z2. Okay, minus 4z3 plus 6z2. And so on, until we have replaced everything here with that central difference. So this is the replacement of that. Okay, and then the lambda contains the EI, the mass, the frequency, and the edge to the power of 4, as we saw in the previous slide. So this is for point number 2, and then we do the same for point number 3. So this is going to be 3 plus 2, 5, 3 plus 1, 4, 3, 3 minus 1, 2, 3 minus 2, 1. Point number 4, the same way. We don't need to do for point number 5 because it's 0. And now directly we see that Z1, the displacement at point 1, it's 0. And as we learned before from here, that for simply supported, if it's simply supported, the displacements of this point is the same as this with a negative sign. Okay, so Z0, which lies outside here, is minus the displacement at point 2. Here, this is Z1 equal to 0. And the same thing here, Z number 6, which lies outside on this side, is the same as Z4, but with a minus sign. And Z5 is 0. Okay? Yeah, so this is what we saw before, how we get the relation between what's inside and what's outside for the simply supported. So now, considering these, we can simplify the equations, the 3 equations for the points, for the internal points on the beam to this. And this we can write in a matrix form. This is Z4, Z3, Z2. Okay, Z2, Z3, Z4. So 1 Z4, this is the 1, minus 4 Z3, plus 5 Z2. Okay, and here, minus 4 Z4, plus 6 Z3, minus 4 Z2. And here, 5 Z4, minus 4 Z3, and 1 Z2. Okay, so this can be written like this. And this is the matrix that we saw before. Here, this is exactly that matrix. Okay, that where the C1 is always 5 and the C2, C3 always 6. Okay, so if you have a simply supported beam, and you divide it in 1,000 points, it will be the same. It's just like this will be 999 by 999 point matrix. And it will have these diagonals and off diagonals. The first and the last is 5. All the other diagonals will be 6. All the off diagonals, first one minus 4, the second one will be 1s, and the rest in the matrix will be 0s. Always. Again, if you have a clamped boundary somewhere, you would have to consider, instead of considering that the moment is 0, if it's a clamped, you have to consider that the moment is that the slope is 0, and you get the relation between the inner and the outer points, and then you will have other numbers at the ends where you have, if you have a clamp, then you will get a 7 here. So if you have clamped, you will have 7, 7. If you have clamped free, you will have 7, 5. Okay? And this is an eigenvalue problem where you have the mode shapes, 3 mode shapes, and you have 3 frequencies that you will get in the lambda matrix when you solve this using the Eich function in MATLAB. So it's a quite straightforward way of analyzing this with the finite difference. And it's actually extremely powerful method. In my licentiate thesis that I did in 1996, I analyzed cable state bridges in a dynamic vehicle bridge interaction problem that we will talk more about on Wednesday, using the finite difference method, idealizing a cable state bridge with a beam on elastic foundation and analyzing it in this way. So it's you can do quite complicated things with the finite difference method. And this is what you will do for the problem of today. I will describe more the problem B1. So I have a question here. How do you get the Z6? Well, the Z6, you get the Z6 in exactly the same way because it's simply supported. You can apply, it's simply supported. You have a 0 moment at M6 is equal to 0. In the same way, you replace the derivatives and you will get in the same way the equation saying that Z6 is equal to minus Z4. Okay? You should try this on your own, and you will see that it works out the same. I have another question. Not sure, but I think Z6 doesn't exist because there is no node. Yes, so Z6 is a fictitious point which lies outside of the beam. You will always get, because you see these central difference approximations. Using these, you will always get points outside of the beam. If J is the point where you have the boundary, for example, of the beam, where you have the simply supported, in this case, if you're approximating this, you will get points outside and points on both sides of J. So if J is the last point on the beam, you will get J plus 2, which is outside of the beam, and J plus 1, which is outside of the beam. Okay? So you will always get points outside. If its moment equals 0, then it's this one, this equation, moments equal 0, and then you have 1 point outside of the beam. If it's if it's the slope, then it will be d to the power of 3, d3z to x3. You have to get the approximation. I don't have this equation here, but you will find it in the textbooks or in the handbooks. So you have to use that to get the slope, and then it will give you, if you do the derivation, you will see that you'll end up with a with a 7 instead for the clamped end. Okay. Okay. So for the exercises B1 to B4, you will be working on this bridge, which is a bridge built in 2005 on the Bothnia Line. It looks very simple, but it's actually, the behavior of this bridge is very complicated, even though it's a simply supported bridge. It's on a straight line. There is no twisting, no curvature. And it consists of two beams, two steel beams, and in composite action, working with a concrete deck, and it's ballasted. Okay, the length of the span is 42 meters, and we have been working on this bridge since 2003, about 2003, 2004, because when the bridge was built, it was built according to the previous code of practice in Sweden, which says that the dynamic factor for railway bridges should be a simple formula, calculated using a simple formula that I will show you on Wednesday. And at the same time, this bridge is designed for speeds over 250 kilometers per hour. This should be in the future. This bridge should be in the future be able to carry trains passing at 250 and more. Now, in reality, if you do the analysis of this bridge, not using this dynamic factor, but you do the proper analysis, you will find that already for speeds below 200 kilometers per hour, the bridge will experience resonance for long trains. And this is what you will see also when you do exercise B2 on Wednesday. So we started investigating the behavior of this bridge using sensors and FE models and so on. And also trying to come up with a retrofitting method to include, for example, dampers on the bridge. So in the future, when we want to run trains at higher speeds, we will be able to do that without having vibration problems in the bridge that can lead to ballast instability, that the ballast will start to move and the track will get unstable, or that can lead eventually to fatigue problems in the steel due to the high vibrations and deformations. So that's why we find this bridge interesting to study. Actually, the last week of September, we are going up to the location of this bridge, and we will instrument that bridge, as well as also another bridge similar to it, a few kilometers away, which is called Bring On. We will instrument them, and we will also put dampers on these bridges. So for those of you who are interested to do a master thesis connected to this, to the test that we will do, feel free to come and talk to me or call me or email me. It will be Andreas Andersson. I think most of you know Andreas, my colleague who was responsible for the FEM course in the spring. So he will be responsible for conducting this vibration test on the Banafiel and on the Bring On bridges in September, last week in September. We have according to the drawings, we have all the properties that we need. The E-modulus, it's steel with a concrete deck, but we can calculate this as an equivalent steel section. Doing an equivalent steel section will give us moment of inertia of 0.62, an area of 0.57. This is the mass of the bridge without the ballast. The density of the ballast, the height of the ballast, and the width of the ballast. So it's a single track bridge. There's only one track, so the width is 6.2 meters. Now, you have to include the mass of the ballast, of course, in this. And this is something that you'll have to think of when you do the modeling. How can you incorporate the mass of the ballast? I can give you a hint. The easiest way of doing it is to calculate an equivalent density, because you have an area. This area includes the steel and the concrete, an equivalent section area for the steel and concrete. And this is the density of the ballast, and you have the density of the concrete, but you will have to consider an equivalent density for the whole structure, which include also the ballast. So when you get the frequencies, you will consider the mass of the ballast as well in the frequencies, not only the mass of the deck and the steel beams. Okay, and the exercise B1 consists of 2 tasks. The first one is very easy, because what you will do is exactly what I showed you on this simple beam, which was divided in 4 segments. You will do exactly the same way. You will divide this into 7 nodes with 6 segments. And you do this by hand on paper, and then you will create this A matrix, and then you will solve this using the Eich function. When you have solved it using the Eich function, you will get the frequencies of the first vibration modes. You can compare these frequencies with the exact solution. And with exact solution, I mean the solution that you get from this table. So simply supported beam, you have the frequencies, the lambda value 1, 2, 3, and you have the equation for that here. So the frequencies you get from the MATLAB Eich function, which is approximate, of course, because you only had 6 segments, should be compared with this. This is the exact solution. Okay, that's task 1. Task 2 is more tricky, because here you will have to write a MATLAB program that can do this for you with the number n of the segments. So you can write a more general code that you can test, because if it's 6 segments, you can do it on hand, on paper. If it's 600 segments, you cannot do it on paper. Okay, you can, of course, if you want, in weeks, but otherwise you can program this for a general number n segments. So the question is, how can you enter this in MATLAB for n-1 by n-1 number of segments? So there are different ways of doing it. I want you to think before you start programming. The easiest is probably to create an A matrix of this size, which only contains zeros. Okay, and then you start filling in. You use 4 sentences to fill these diagonals with 1, and these diagonals with 4, and then you one by one you create you fill these cells in the diagonals, depending on all of these are 6 and these are 5s. Okay, so but you will need to think a little bit. So this is the demanding part here. I think it's a matter of like programming this in MATLAB. It's easy to do on paper, but to come up with these 4 sentences to get the A matrix can be a little bit tricky. But then when you have done this, when you have your code, you can of course first test it with 6. You enter n equal to 6 and just see that you get exactly what you got here when you did it by hand. And then you can do it for more number of segments, for 10 segments, 40 segments, 50 segments. And then you can calculate the eigenfrequencies, and you can make plots. For example, you have a plot On the x-axis, you have the number of segments, 5, 6, 10, 20, 50. And on the y-axis, you have the frequency in hertz. And you have one curve for frequency number 1. You have another curve for frequency number 2, another one for frequency number 5. And you can see then how many segments on the x-axis do you need for the frequency to converge. Okay, so you see that the frequency is changing. If you look at F1, it's changing as you increase the number of segments from 5 to 10, but probably from 10 to 15 to 20 to 30, it will stabilize and it will not change. But you will see that the higher the frequency order, frequency number 10 will probably need more segments to converge. And it's not so strange because frequency number 10, the higher the frequency, the more bouncing you will have in the mode shape, which means that you will need to discretize the beam with more segments. The first frequency, which is one sine, it will be easy to describe with few segments. But the frequency number 10 will have several sine waves. It will not be able to approximate this with few segments. You will need more number of segments. And this is something that will be obvious when you plot this convergence plot. Okay, and then also in task 2, the last question is how many segments do you need to get a good accuracy of, like, say the 10th with two correct decimals for the 10th frequency, so F10. So how many segments do you need? So I think this will be quite easy when you have done the MATLAB, the simple MATLAB code here. When you have done this, then this is a matter of running the code and plotting nice results and putting them in your handout. Okay, let's see. I have a question here. Can you please upload the example on Canvas? Okay, I'll do this. And then we have a question about the bridge. Was the formula according to the old code just wrong or not designed for high speed? Okay, so this is what we will talk about on Wednesday. The formula which was used actually up to year 2000 something, 2003, 2000. This formula does not consider resonance. So this formula only considers the additional dynamic effects outside of resonance. At resonance, we will see that we will have to make more complicated analysis to consider resonance. So both the Swedish design code as well as the Eurocode were updated for about 20 years ago to consider the high-speed trains coming in Europe. And this is still a huge subject for research. So we have 5 PhD students currently in the division working on this. So I think you have met some of them. Abbas was helping you in the FEM course. He's studying the influence of soil structure interaction. So how can you include influence when you're analyzing these bridge models for high-speed trains? How can you consider the contribution from the soil? Because the soil itself will contribute to damping, and it will also contribute to added mass. So part of the soil will be actually also bouncing with the bridge and the different mode shapes, which contribute to added mass. And we know that if we increase the mass, we will decrease the amplitude of vibration. That is also something we talk about on Wednesday. So that's Abbas. We have also Johan Östlund, who's also working on developing methods of analysis of end-shield bridges, Endhamnsbroar in Swedish, for high speed. We have Sara. Sara Tell is working on developing dampers for high-speed railway bridges. So we have Reza that you have as an assistant. He's working on, he's developing the next generation probabilistic codes of assessment in Europe. So, so his work will result in new formulas that can be used in the future for speeds probably up to 400 kilometers per hour or more. So it's still a very large research area, and every year we have at least 2-3 master thesis projects connected to this. So if you find this interesting, talk to any of us about possible work for master thesis. Okay, more about this on Wednesday. Do we have any other questions? This was actually all what I had. It normally takes more time because I normally do all the derivation on the board, but it's more difficult to do this in Zoom. So yeah, if no other questions, I will end the lecture here, and hope you will enjoy the exercise B1. Thank you and goodbye. Have a good day.